Hello everyone, welcome back to the channel. This is the fourth session of the Math for Machine Learning series. So far, we have covered linear algebra, where we discuss how data is represented. Then we discuss about probability and statistics, where we discuss how model handle uncertainty. And last, we discuss about calculus, where we discuss how we measure the changes. Today, we connect everything together like how linear algebra, probability and statistics, and calculus uses in machine learning model. Today's topic is optimization and gradient descent for machine learning. If you have been following the explosion of artificial intelligence lately, from ChatGPT writing poetry to self-driving cars navigating streets, you might have wondered how does pile of math and code actually learn to do anything? We often hear phrases like training a model. But what does training a model means in physically? Does the computer sit there and read the textbook? No. Training is actually just a loop process of making mistakes and correcting them by step by step. Today, we are going to look under the hood of almost every modern machine learning algorithm. We are going to explore the engine that drives learning. It's a concept called the optimization, and its star player is an algorithm that's called the gradient descent. So the goal of the optimization is the minimizing the mistakes. This is the goal of our today's session. So let's dive in. First, talk about the optimization. So what is optimization? So optimization means finding the best possible value of a function. In machine learning, it is simply the process of finding the best possible version of our model. So we want the model to make the least amount of mistakes. Means the model should be accurate. So you can think of it like this. If you are trying to hit a target, you just adjust your aim after each throw, right? You are optimizing your throws to hit the bullseyes. So you see, like this page image. In the image, the children try to hit the target by the ball, but at the beginning, they lost to hit the target, like you see. And but by their continuous progression, time by time, at the end, they can hit the target. So this is the optimization. They can hit the target at the last time, like first they are high error and low accuracy, and at the end they get the low error but high accuracy. This is called the optimization. In machine learning, our target is to make predictions that are as close to the actual answers possible. Our aim is determined by the internal settings of our model, which we call the parameters. So we can also understand it by this curve. You see, this is the ball shaped curve, and if we throw a ball from this point, like we throw a ball from this point, so it want to be the one to the downward like this. So this is the lowest point. This point is the lowest point. Like if you clear the ball, this point is the lowest point of this curve, and this is our target where we ball the goals. If we throw a ball like this from this point, you see, we throw a ball from this point, and it will come this lowest point, but by passing many steps, you see, if we throw another ball, it come to the lowest point, but it come to this point by passing many steps. This is the steps, and this is the learning step for this ball, like the children hitting the target. So this is the optimization for this ball. So that's how the optimization works. So optimization is finding the best possible value. So when is the finding the best possible value um, for our model in machine learning? So the function is the loss function, and the goal is the minimizing the error. So then we discuss about the loss function. So what is loss function? There we see the function of the optimization is the loss function. So now we discuss about this loss function in the next step. So loss function is just measuring the mistake. So you see, before we can optimize something, we need a way to measure how bad our model is doing. So if we know the model well, how bad it is doing, then we optimize the model and then get the best possible solution for this model. So this is where the loss function comes in. Let's understand it by an example. Like, suppose we want to build a model to predict the house prices. The true prices of this house is 2 lakhs dollar and the predicted price is $180,000. So 1 lakh, sorry, 1 lakh $80,000. So there is an error. You see, there is an error. So the error is the difference between them, like which will be the $20,000, which is the 2 lakhs dollar minus $1 lakh $80,000. So the difference between them is $20,000. So which is a big error. To measure this error, we use the loss function. It's a mathematical formula that calculates a single number representing the total error of our model's predictions. So the formula is the loss equals to y minus y cap whole square. So where y is the true value, this is the true price of the house prediction. So and y cap is the predicted value, which is predicted by the model. You see, so you can see say that why you use the square. We use square because of removes of the negative sign and punishes the big mistakes more. We discussed it about our previous session in the calculus. If you want to see, you can go to the calculus session and see it in briefly. So if prediction is far from the actual value, it creates the high loss, and if prediction is close to it creates small loss, close to the actual value, it creates the small loss. So if a high loss means our model is making many mistakes and a low loss means it's performing the very well. So our goal is in optimization is to make this loss number as small as possible. So these are goal in optimization. So if we plot the loss against model parameters, so we usually get a curve shaped like a bowl. This is the bowl shaped curve. This is the bowl shaped curve. In x-axis, this is the model parameters, which is y-axis, and in y-axis, this means loss. This is the loss, and the lowest point of this ball is the best model, which is the global minimum. This is the global minimum, and this is the best model ever. So we discussed it about briefly in our previous session, which is calculus for machine learning. We give a basic idea in this session. So this is the point of this for the this is the point of loss function, and you see this is the point, and if we throw a ball, these go to the step by step. Once it go to this point, means in global minima, this means the model or the ball has zero error. So the model come this point by step by step, and if when the model goes to this point, came to this point, this means the model is now in global minimum and the model has zero errors. So that's how it works. So so this is the loss function, how it works. Next we discuss about the gradient descent. So how do we actually reduce the error occurred by the loss function? We see in the previous bio optimization, we want to we first we want to get to the loss of this of the model, so the loss function of this model. So now we discuss about how we actually reduce this loss function. So that is where gradient descent comes in. Imagine you are standing on a foggy mountain and you can't see far. You want to get the very lowest point of the mountain below. You can't see the whole mountain, but you can feel the slope right where you are standing. To get down, you have to take a small step in the direction that feels steepest downhill, right? In machine learning, this steepest downhill direction is called the gradient, which is slow. The slope of the mountain is the gradient. Remember that. This is the very important point of gradient. The slope of the mountain is the gradient, which is the steepest downhill direction. So gradient descent is an algorithm that repeatedly calculates this gradient and then adjusts the parameters and the and adjusts the parameters to the mountain in the opposite direction and towards the lower loss. So now we can say that why in the opposite direction. So let's understand it. So basically to get down, we calculate the slope. I said that before to remember that we go to the downhill for calculate the slope. So from calculus, we know slope is called the derivative. You know, this slope is the derivative, and for the higher dimensions, we call it the gradient. We call the grad slope the gradient in higher dimension. When you use the higher dimension, we call the slope is gradient. So gradient is the derivative of the loss function. So gradient is the dDW of loss. This is the derivative of loss function where the gradient is works. So the gradient tell us in which direction the loss function increases fastest. So in which direction the loss function they increases fastest, in which is the gradient tell. So there by this we know that in which direction we know which slopes the loss function increases repeatedly. So you see that if we in there if the loss function is increases repeatedly, the model is occurred the big error. And if the model is occurred the bigger error, there will be high loss and the model makes many mistakes. So we should want to reduce these losses. So if we want to reduce the loss, we want to go to the opposite direction. So you see, to reduce the loss, we go to the opposite direction because we want to get the best possible solution for this model. So we want to reduce the loss, we want to reduce the loss, we want to go to the opposite direction of the gradient. So let's understand it the by an animation like this, you see. So if we play this animation, you see the ball is goes to from this point to this point. There you see this is the point where gradient the direction in this point the direction of the gradient is this direction, but the ball but this is the lowest point of this ball shaped curve, and this is the target. So if we want to go to the target, we should go to the opposite direction of the gradient, of the slope of the gradient. This is the tangent. You see, this is the tangent of the gradient. You can also see that if we want to you see in the slope, if we replay this sequence, you see the slope is increases repeatedly. This slope is increased repeatedly. If we replay this session, in this point the slope is 0, and there the slope is increased repeatedly. So we should want to reduce this slope. So we should go to the opposite direction of the gradient to reduce the loss and get the best possible solution for our model. So So in gradient, to reduce the loss, we go to the opposite direction of the gradient. So that's why the update rule looks like the new parameter equals to the old parameter minus learning rate into gradient. there where the gradient comes. So new parameter, what is new parameter? This is the new parameter for our model, and because we optimize is step by step. So the new parameter will be equals to old parameter, the previous step of the model, old parameter minus learning rate. So learning rate into gradient. So the new parameter w equals to the old parameter w minus alpha, where alpha is the learning rate, and into the gradient. The gradient, we know the gradient is the derivative of the loss function, so the gradient equals to ddw into loss. So w equals to w minus alpha into ddw of loss, where w equals to the model weight which you want to get, and alpha equals to the learning rate, which is step size. We discussed it before. The ball want to go to the lowest point, and the step of this ball is the learning rate. So, and gradient is the slope. We discussed it before. This is the slope of the mountain, the slope of the mountain, the steepest possible direction, and the steepest downhill direction is a slope, and this is the gradient. So that's how the gradient works. And this is the formula of gradient descent, and this single equation powers the modern AI. So you see, alpha is the learning rate, means it is step size. So what is learning rate we discuss about it in briefly. So learning rate. So learning rate the controls how big a step we take each time. So you see in this image, if we clear all the ball, if we throw a ball from this point, the ball onto the this point means the downhill. But so you see, if we throw the ball, it go to the downhill by passing through some steps. So these steps are the learning rate. So you see, if we from this point throw this point, the ball go to the small steps, and if we throw this point, the ball passes through the big steps. So what this means, you see, there are three possible cases. Case one is if the learning rate is small, so means the alpha is too small, then the steps are teeny. Like if we understand it by this, if the learning rate is small, means the steps are tiny, the training becomes very slow. The steps are tiny from coming to this point to this point. The if this person want to come to this point, there will be take much times for taking the small steps or teeny steps. This is so the trainings becomes very slow. And if the learning is large, like if alpha is too large, we overshoot it. Like you see, the if the person comes to this point and take big steps, he, it he will come to this point rather than goes to this point for taking the big steps. So the model jumps around and it may never coverage for this point. And the case three is if the model take the proper learning rate. With proper learning rate, we smoothly reach the minimum. Like if this person take the proper learning rate, so that this person goes to the global minima in the moderate steps, and this is the optimal convergence. So we understand it by an animation. Like you see this animation, this is a learning rate demo. Like if we take the small movement, you see they take much time. Like this, we clicked it, you see the ball comes to this point, takes much time, and the learning rate is too small, 0.02, and the ball takes the maximum steps, which is 17, to come to this point. The ball cannot come to this point for the max steps reached, so cannot came to this point. But then if we take the big jump where learning rate is high. You see this point, the ball is jumping around, but it can go to the minimum steps. It overshoot. So that's why this reach the max steps, which is 17, but it cannot come to the lowest point for, and it overshoot the steps. And then if we click to the perfect movement, you see it came to the lowest point by the minimum, lowest point by one steps. You see it comes to the one step, discovers to minimum. So it is the optimal learning rate, and it is the efficient convergence. So we should get the perfect learning rate for a model to overshoot anything. So choosing a learning rate is extremely important, because without choosing learning rate, we divergence our target. Like if we tell about further, so we have like this one. If this man takes small steps, it will be much more time to come to the global minima. If it take the too high steps, it will overshooting or unstable, means it maybe cannot come to the global minimum. And it if it take the right steps or optimal convergence, it maybe takes it can came to the global minima at a perfect time. So that's how the learning rate works in gradient descent and optimization. So choosing learning rate is extremely important for every model, you see. So now we discuss about the types of gradient descent. So we discussed about the gradient descent before. So what is gradient descent? Gradient descent is an algorithm that repeatedly calculates the gradient and then adjusts the model parameters, means our position in the foggy mountain on the in the opposite direction towards the lower loss, means gradient descent to optimize the gradient, to minimize the model's parameters, means adjust the model's parameters in the opposite direction of the gradient, because we want to reduce the loss function we did previous in the loss function there. And now we discuss about the types of gradient descent. So there are three main types of gradient descent. First is the batch gradient descent. So in batch gradient descent, the gradient descent in this, they took the all data sets and give the output. But in this, that the gradient descent, the output is stable, but it is very slow. But we want to take the model very fast. We don't want our model take the very slow for taking the all data sets. So next came to the SGD, means the stochastic gradient descent. So in statistics gradient descent, they are use one data point and give the fast value. But in this, because of this give the fast value, it much noisy than others. So this is usable, but it's noisy. So we decrease them and came to this point. This gradient descent. This is the mini wedge gradient descent, and this is the most used. So why it is most used? You see, they are uses the small batches. The mini batch, you see the name is mini batch, so it is used the small batches, and for the use of small batches, it take balance of speed and it takes the stability. So it for balancing its speed, it came to the stability, and it gives the perfect value for a model. So modern deep learning almost always uses the mini batch. So modern deep learning model is uses the mini batch gradient descent, because it's is give the balance of speed and give the stability because of use of small batches. So sometimes the mini batch gradient descent also use the SGD, which is stochastic gradient descent, because it fast. So sometimes the machine learning modern deep learning model use this together, but this is the main gradient descent to use in model deep learning model, which is the many wedge gradient descent. So these are three kinds of gradient descent: best gradient descent, stochastic gradient descent, and mini batch. Batch gradient descent use all data set, but it's stable but it's slow. So we don't use it. The stochastic gradient descent is use one data point. It's fast, but it's very noisy compared to other gradient descent. But in mini batch gradient descent, it is balance speed and it is also stable for user small batches, so it is most usable gradient descent in all of three kinds. So that's how the gradient descent is used. So there's the gradient descent. So now we discuss about the optimization in linear regression. So how optimization used in linear regression? You see, let's connect theory to practice. We So linear regression model is equals to y cap equals to wx plus b, which is studied in linear algebra session. We studied it in linear algebra session, the linear regression, where y cap is the most possible value x, the y cap is the output or the predicted output which you want to predict or which is the model want to predict. This is the predicted output which is y cap, and x is the input we give to the model, the data we give to the model, and w is the weight or slope, like we learned in the linear algebra session equals to y equals to mx plus c, where x is the input, m is the slope, and c is the intercept, and y equals to the output. There we compare to this from y equals to mx plus c. So there is y cap also the output or predicted output, x is also the input, and m is the slope. They are in machine learning model, they are w equals to the width, and b is the bias or the intercept like C. So they are linear regression. We talked briefly in the linear algebra session. So next, the loss function. So loss function L equals to y minus y cap whole square, where y equals to the actual value and y cap equals to the predicted value. We discussed it in the loss function session. In the loss functions, so where we use square, we use square for accepting the minus to plus, so we use the square of for. So in this we want to reduce the loss, and there in optimization we read the loss functions that we want to reduce the loss by optimization. So the loss function usually depends on the w and v. You see, the loss function depends on the y cap, or means the predicted output which we get from the model, and this y cap is equals to wx plus b. So this y cap depends on the w and v, and so the loss function also depends on the w and b. So loss function depends on the weight and the bias. So we ask the if we change w a little, does loss increase or decrease? And or we can say that if we change the b a little, does loss increase or decrease? Means if we want to change w a little, the L will be increase or decrease, or if we change the V, well, the bias change a little, will be the loss function is increase or decrease. So that's how the loss and linear regression are works together. In derivative of derivative of W and V tells us which direction to move and how steep the slope is. So for by the derivative of w and v, which is depends on which is depends on the loss function, means the loss function depends on the w and v derivative of w and v. So this w and v tells us which direction to move and how steep the slope is. So this tells us low to adjust the parameters. tells us how to adjust the parameters. For adjusting the parameters of the loss function, we use the derivative of w and v. So we should repeat this process until loss becomes small. We mean this means the learning. So why we repeat this process? Because if we change w a little, the loss will be increase or decrease. We change the b a little, the loss will be increase or decrease. So we want to get the minimum losses. You see, we want to get the minimum losses. For get the minimum losses, we change the w and b repeatedly, one by one. So this is the learning. For change this w and b, this is the optimization, and this is the learning step of this optimization process in linear regression. That's how optimization used in the linear regression. So linear regression also connect to the optimization. So next we discuss about how optimization is in neural networks. So you see, neural networks are just large mathematical functions. So line, so training steps means the forward pass, which is compute the prediction and computer loss, and backward pass and the compute gradients. You see, the neural networks are just and training steps means the forward pass. Forward pass means the computer get the prediction and the computer compute the loss. And in the backward pass, the computer compute the gradients and update the weights. So in this backward pass uses the partial derivatives and the chain rule. So we discuss about the partial derivatives and chain rule in the calculus video. You see, the partial derivatives, we discuss about it, like you see the partial derivative dy dx equals to dy by du by into y plus into du into dx. That's how the partial derivatives works. And the chain rule is if the function is very large, we discuss about it. If the function is very large, we 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 do the derivative step by step. So for the step by step or part by part, for doing the part by part, the derivative will be very easy. So there we use the chain rule. So there in this chain rule, we discuss about that in neural networks there are many module works together. So by using chain rule, if we do the every module step by step or part by part, there will be very easy to get the output or calculate the model. So that's how the chain rule works in the model. So that's how calculus works in the model. And calculus works in the model or neural networks, and that's how the optimization works. Means, so by chain rule and partial derivatives, we optimize the model using the neural networks, and that's how the calculus used in optimization. So why optimization is the core of AI? So without optimization, there is no training, no learning, no deep learning. So why there is no training? You see by this, like if we don't use the optimization, there is no slope. Like when we came to the foggy mountain step by step, if there we don't use the optimization, we don't know the steepest downhill direction. So if we don't the steepest downhill direction, we cannot get the learning rate, and if we don't get the learning rate, we don't chain us. Like the ball want to get get this, like the ball want to get this point, the lowest point. So the ball go to the this point by step, and this is the learning rate. By the ball want to get the training, or if we want to get like in this image, like you see in this image, the the children wants to hit the ball in this target, but they first they cannot hit the target, but by time or by optimization they hit the target in one time, and that's how they hit the target. And this is the learning step. This is the learning step by came to the high low accuracy to high accuracy, by high error to low error. So this is the train by them by hitting the ball. So this is the optimization. Without this optimization, the model cannot get the training itself, and the model cannot learn how to train itself, and there is no deep learning. Because if there is no optimization or there is no learning or training, there is also no deep learning. So optimization is the engine of machine learning. So that's the optimization is the core of AI. It is the engine of machine learning. So we learn in linear algebra gives the structure, how the structure a model. Like in linear equation we get the equation y equals to wx plus b. Like we also discuss about many linear equation in the linear algebra session. So linear algebra gives the structure, and probability gives the reasoning, like the under uncertainty, because probability is the uncertain, so works on the uncertain value. Like if we discuss in the probability, like there are many red balls or white balls. If we take a red ball from there, which will be the probability of getting the red ball come to the red ball. This is the probability, this is the uncertain value. The red ball came or not, a white ball came or not, this is the uncertain value. Their probability works in this uncertain value. So that's how the probability work in the machine learning model. So then we discuss, then the calculus gives this change. So how the model changes parameter one by one, like the model changed by the derivative or by the slope. We know the slope of equation is the derivative. So this is the calculus. That's how the calculus helps to train the model one by one. Without the calculus, the model cannot train. Like we also discussed it about this session, like in the slope, in the learning rate, or in the gradient. We discuss about a model. We discuss about like when we went to the foggy mountain to downhill, we get the slope or steepest direction, downhill direction. This is the slope, and this slope is the derivative, and this slope in the higher parameter tell is the gradient. So this is the gradient where use the calculus. So what is the gradient? Gradient is the derivative of the loss function. So this derivative is the calculus. So the gradient also attached to the calculus. So that's how the calculus also works, and the optimization turns all of it into learning. Like optimization turn the linear algebra, probability, and calculus turns all into this learning. We see this in this session. Like first we see the series, where like you can say where linear algebra turns into optimization, like linear algebra turns into optimization in linear regression. We discuss about it. This is the linear algebraic function, and this is the thing how optimization works in linear algebra. Like probability also work there, like in prediction, making prediction, like house prediction and many things. And prediction, the probability works. So where the calculus works there, this is the things where calculus works. This is a derivative. There are also many steps where calculus works. We don't go to the deep now. We discuss about this, and this is where the gradient descent, there also calculus works in gradient descent. So because the gradient is the main thing is the gradient is the slope. So that's how the calculus works. So optimization turns all of it into the learning. All calculus, linear algebra, all probability and calculus turns it into the learning. So that's why the optimization is the core of AI. Without optimization, the model cannot train, learn, and cannot turns all of linear algebra probability and calculus into the learning. So that's why the optimization works in AI. And optimization work use the gradient descent to turn all of it into the model. So by using gradient descent and optimization, the model turns into the less error and we get the better output. So that's all for today. So today we discuss about optimization, which is minimizing loss, because by optimization the model practice more and more. The model train itself by learning, by increasing learning rate. So the model can get the minimizing the loss. Then we discuss about the gradient or direction of steepest increase, like want to go to the downhill of the foggy mountain, the direction of steepest increase, and this is the slope and this is the gradient. So we also move to the opposite gradient to reduce the loss. So when we move to the opposite direction to reduce the loss, we want to move the opposite direction to reduce the loss because of we want to minimize the loss, because gradient is the derivative of the loss. And if we go to the direction of the gradient, the loss function, the loss of function, it will be increased, and the model gives us the high error. So you want to reduce this error or reduce this loss function. So we go to the opposite direction. So learning rate controls step the size. So learning rate is the let's say change the model by step by step. This is a step size. If we get if we take the small step, the learning rate will be very, you see, this is the if we take the small rate, the step will be tiny and training becomes very slow. If we take the large step, and the learning rate will be overshot, and the model will be jumps about around and never, it will never coverage, or it will be never go to the global minima. If we take the proper step rate, we smoothly reach the minima or global minima. So that's how the learning rate control the step size. And mini batch as it is widely used. So why mini batch used? You see, we discuss about batch gradient use all data but it's slow, and SGD use one data point, it's fast but it's noisy very, and but in mini batch gradient descent, it uses small batches and it balances speed and it also give the stability. So every machine learning model use the mini batch SGD, so it is widely used. So now with this video, we now have a complete mathematical foundation for machine learning, because in machine learning mathematics there are use of linear algebra, probability and statistics, calculus. This three is the main basic topic for the machine learning mathematics. We covered all these three basic in previous three session, and today we talked to about the optimization, which is the main core, and it takes of these three, linear algebra, probability and statistics and calculus, and the dive together, and it turns all of it into the learning. So we covered all these three and the optimization in this session, and that's how the mathematical function like linear algebra, probability and calculus works together, and optimize them and works the process to works in the machine learning model, and it turns all of it into the learning. So that's all for today. If this sessions this helped you, then like, share and subscribe, and thank you for being part of machine learning mathematics. I'll see you in the next session. So thank you everyone, thank you for your time, thank you, bye everyone, See you in another session. Bye.